Assalamu alaikum, everyone. And again,
Walaikum assalam.
once again, welcome to today's session. So this would be probably the last class before the Eid vacation. So let's try to start and finish it and then enjoy our Eid, okay? So in Indonesia, when is the Eid, Aldi?
On 20th, sir.
Oh, like Saudi Arabia?
Yes.
Okay. Okay, so in Bangladesh, we have on 21st, probably no one from Cameroon could join because the timing is not, that good for them. Probably it is around 3 at night right now. Okay, so let's continue. So in the last class, we were actually looking through the process of building the phasor diagram for the single machine infinite bus system having a synchronous machine, which is third order dynamic model. And we also saw how to calculate the initial conditions. And specifically, we looked at these values like the initial value of delta. That's the delta naught. Then we also found the initial value of EQ dash along the process. We also found the DQ components of the phasors, current phasor like ID and IQ. The DQ component of the phasor, the terminal voltage of the generator, that is VD and VQ. The DQ component of the infinite bus voltage, which were VBD and VBQ. And we also actually cross-checked the obtained values by recalculating the PT, the QT, and the magnitude of VT. So most probably we actually went through these, and also we cross-checked the values of ID and IQ. So one set of values of ID and IQ and VT, these were, so VT, PT, and QT, these were actually given to us at the initial phase before solving the problem of initial value calculation. And then we took help of the phasor diagram to find out all these. And then we again cross-checked by recalculating ID, IQ with some different formula, okay? So this was the, from the phasor diagram, these were using some other formula where ID and IQ were depending on the values of values such as the EQ dash, the delta naught, VBD, VBQ, etc. So all these we can also assume to be their initial value, okay? Without loss of generality, we can use a naught at the subscript just to represent that this is the initial condition or this is the initial operating condition, all the same. With the initial values of PT0, QT0 were given, and also VT magnitude was given, and this was actually the same as, so this will be IQ0. So today what we will try to do after calculating all those and after coding it in MATLAB, we found that, well, the calculation process was okay. It was correct. After after the cross-checking, we found that it was correct. The validation was done. So now what we will try to do, we'll try to simulate the system and try to find out the delta versus time and the other variables versus time. In other words, we can say that we have some differential equations. We would like to apply some numerical integration technique just to get these values listed here. Omega versus time and any other variable of interest. It could be state variable, could be anything as a function of state variables. It could be also PT versus time. So we will see that once we can calculate, once we know the state variables trajectories, then we would be able to calculate the other required values, QT versus time, and some other of your interest. Of course, VT versus time, VT magnitude versus time. So these would be the target. And in the last part of the last lecture, we actually went through the process, one of the numerical integration techniques that we are going to adopt today, and that was the Euler's method of numerical integration. But before that, let me actually finish the initial value discussion part, because some values are still left. If we look into this block, we know that our state variables are 3 here. For this model, we have 3 state variables. So let's go through the questions then. First question, do we know the initial value of the first state variable, delta? Yes, we know. So that is done. Next question, do we know the initial value of omega? We don't know yet. So what we can do, other than calculating or obtaining the phasor diagram, calculating all the other variables, we still see that, well, we have some or few more variables to be calculated. And one of those is this omega, okay, which is a state variable because it has the differential operator here in the second equation. Whereas omega base is a constant, which should be taken as 2 pi f, where f is the base frequency. Usually we can take 50 hertz. So can anyone say what would be the value of omega here in steady state or the initial equilibrium point? Can we find the omega initial value from this equation alone? The left-hand side is simply d delta over dt. Under steady state, what would happen to this? In steady state, what would happen to d delta over dt? Anyone? Okay, what is the meaning of steady state? And what is the meaning of dynamic state?
Steady state means constant.
Steady state means constant. I mean, constant, what is constant? Who is constant?
Who doesn't change its value with time.
It doesn't change its value with respect to time. Excellent. So what does that mean? So that means if delta is a variable and it is expressed, let's say we are looking for its variation with respect to time by this differential equation. So when I say that the system under this block, within this block, is in steady state, okay, so it means that all of its dynamics related to this delta dot, omega dot, and EQ prime dot, all should actually be considered to be equal to 0. Okay. So if it is in a steady state equilibrium, then d delta by dt should be equals to 0. And that means omega equals to 1. Is it okay? That means you make the left hand side equals to 0. So omega base is a constant, so you can divide 0 divided by the omega base, and that leaves you with omega minus 1 equals to 0, and ultimately you get omega equals to 1. So that would be your omega initial. Clear? Okay. What about the second one? Let's try to use the second one and try to extract some more information about our system. We also make it equals to 0 because it is a steady state. What will happen to this in steady state? We already found that in a steady state, omega is equals to 1. So this part would go to 0. So in a steady state, there is no damping effect. So you see, this d is the damping coefficient or damping power coefficient, whatever you say. This is damping power coefficient. It means whenever there is any speed deviation in the system for the synchronous machine, there will be some damping effect. Okay, there will be induction machine effect or induction motor effect, and due to that, there will be some damping torque. And that damping torque is actually modeled by this d multiplied by omega minus 1. So in general, the damping torque is represented by PD equals to d delta over dt. Okay. And we can also write it like d delta by dt is what? It is basically, it represents the deviation in delta with respect to time, or you can also say it is the speed deviation from synchronous speed. So we can also write it like this, omega minus 1, where 1 is basically your synchronous speed in per unit. Okay, synchronous speed represented in per unit, and this omega is the actual speed of the generator. So this one is nothing but what we can see, the one here over here is the same. This omega minus 1 is the same omega minus 1 here. Okay. So this is PD, the damping torque, and that would on or damping torque or power in per unit, they are the same. So in whenever there will be any deviation between omega actual value and the omega per unit value, only then there will be some damping power or damping torque, otherwise not. So in a steady state, omega becomes equals to 1, as we have found here. So this term would go to 0. So what would be left? Ultimately, you will get that PM equals to PE, and this P is nothing but actually PT, your real power output from the generator, the same. So you see that in the steady state condition, we have found another relationship, and that says that in the initial phase, whenever there is no disturbance in the initial operating point, you should have a balance between the mechanical power input and the electrical power output, and that is quite logical. Okay, so you should have a balance between the mechanical input to the system and electrical output from the system. So we can also write now, because we know PT0, so that means the value of PM, which was still unknown before discussing this step. So that mechanical power input into the generator can be also written equal to the electrical power output PT0 from the generator. So PM0 is equals to PT0. This is the outcome from the second equation. From the first equation, the outcome was omega initial value equals to 1 per unit. This is in per unit, remember. So in the whole expression, most of the terms are in per unit except the delta. Delta would be in radians or degrees, whatever you want, you can take. But all the other values like omega, PM, PE, H, D, EFD, TD, O prime, all are in per units. Of course, omega base is the base value. It is not the per unit value. Already I have mentioned omega base is 2 pi F. So other than omega base and delta, all are in per units. So now let's go to the third equation. Let's see what we can get out of it. So again, we write dEq dash over dt. So that should be equated to 0 because it is in a steady state again. Now what do you get? Do you know EQ dash initial value? Yes, we know. XD and XD dash, these are system parameter, machine parameters. So this should be given. ID, we already know its initial value. So from here, we only, so the unknown thing is EFD. We don't know still what is EFD or what is the initial value of EFD at least. So the EFD naught is nothing but this EQ dash plus XD minus XD dash whole multiplied by ID. So these are the additional informations that we can easily get by simply equating the left-hand side or the right-hand side of this equation equals to 0. Okay. So additionally, today, besides the previous calculation in the last class for initial condition, we have also, basically we can say we have continued with that up to now. And that by doing that, what we have found is we have got the initial value of the speed, that is our state variable. We have got the initial value of the mechanical input, and we found that that should be equal to the electrical power output from the synchronous machine. And we have also found the initial value of some scaled version of the VFD. Okay, this EFD is nothing but some scaled version of the originally applied field voltage to the synchronous machine field circuit or rotor circuit. So now we are, again, we can say that, well, we are in a position to apply our Euler method or numerical integration method to solve the problem or solve the system equations. Integrate them and try to find out the trajectories, that is delta versus time, omega versus time, and EQ prime versus time. So let's move forward. Okay. So now let's say in the last class we mentioned about the numerical technique. So now let's say what we should do. Let us rewrite those again, just to remind us. So for any variable x I dot or x dot equal, okay, let me write x dot equals f of x. X dot, this is the generalized representation of the steady space model. X dot equals f of x, where x is a vector. What we did yesterday in the last class is this. We were trying to find out xi plus 1 as the function of xi, where I is the index number or the iteration count, plus delta t, where delta t was the sampling time, multiplied by f of x, where x is equal to xi. So this is basically the simplest way to represent the Euler method. And this is what we are going to do today. We are going to apply it with the help of the MATLAB to our model. Okay. So let's start. We had already built some part of the code, so we will actually continue from there. So let's stop the share here. Okay, so do you see the MATLAB? Is it visible?
Yes, sir.
Okay. So if you remember, we already had this done in the last class up to IQ dash. So today what we will do, we will actually, so this part actually PT1 up to this ID and IQ, these were, we can comment them because these were done just for a validation purpose. So we just leave them out. And we continue with some remaining part of our calculation for the initial value. So we write omega equals to the initial value of omega we found was equals to 1. Then we also found PM was equal to what? Mechanical power input was equals to the electrical power output. And we also found that EFD is nothing but EQ prime plus XD minus XD prime multiplied by IT.
Right.
So these are the additional things that we have included today with our previous code. And besides that, let us also define what is omega base, because we will need it during the simulation. So 2 pi into f. You can write f base. So we have to define what is f. Let's take it as 50 hertz. And what else? We also included some D in our model. So that's the damping power coefficient. Let's take it 0. Because this is in per unit. So let's take it 0.2 or something, whatever, 0.5, just for demonstration purpose. So I think most of the things are done. Okay, another thing we need to do is the definition of TDO prime. Let's take TDO prime is in seconds. It's not in per unit. So keep it in mind, it is in seconds. So let's take it as 5 seconds. And this is the open circuit time constant for the DXC circuit. Open circuit DXC time constant. TDO prime means there is the transient time constant. Okay, the others probably there could be some other parameters, but because these are constant parameters, so whenever required, we will include them, inshallah, in the code. So now let's start the equations one by one. So because it is an iterative technique, So we have to start with the loop, and let's take the counter as the I, and let's take the simulation time is tsim, and of course we have to end the for loop, so we end it initially. So you see that we have to define tsim, the total simulation time, okay, for which I'm going to plot the responses for delta, omega, and eq dash or eq prime. So let's take the simulation time, let's say 5 seconds. Now, because we are going through some iteration with respect to time, we have to discretize this t simulation. So that means we have to define what is our t sample, okay, sampling time or delta t. This is the same as the delta t, and I take it equals to 0.001. You can take it smaller, but bigger would be an issue. So both would be an issue actually. If you go for smaller values, like let's say very small value, 0.000, so it would take a huge time for completing the computation, okay. If you take very small value, then there will be accumulated errors. Remember, the Euler method is one of the simplest method, okay. So there are some inherent errors in calculation if you take, and the error becomes significant if you take this value, the discretization step during the numerical integration. If you take it too big, so 0.1 is actually a very big value, okay, for the numerical integration process. So we try to stay in between. So any value is smaller would of course take a larger time for completing the calculation or completing the simulation. Any value smaller, of course, let's say if you take 1, that means you only get 5 data points, right? For if you take sampling time 1, if you take your total simulation time 5, you only get 5 data points, and that is not sufficient actually to capture the scenario in a very good manner. So we keep, let's say, in between. Either we take 0.001 or 0.001 or 0.0001, something like that. We are taking just for demonstration purpose, so no big deal here. It's not a big deal. So tsim and ts is done. So now actually I should be tsim by ts. Okay. That is because I is the index. I will give you the data points like this. So if this is your tsim, if this is your tsim, and this is, let's say, your any variable, one of the variables, let's say delta. So I gives you actually how many data points you are going to take. Okay, how many data points you are going to take. tsim is the total time, where in this case it is 5. It is 5 seconds. ts is the gap in between each time steps. Okay. So this is ts, the small time step we are taking in each iteration, a small time step forward. So that is the sampling time. So tsim by ts actually will give you these values. This whole bunch of values would be given. So at each data points, we will be actually calculating our delta. Okay, that is our target. At each data points, we will be calculating delta up to tsim. So we'll be getting this much of data points. So my index I should actually take care of all these data points. So that's why it should be I equals 1 up to tsim by ts. So this is I. Now we slowly go into writing the code, remaining part of the code. If anything required, then we'll again go up and fill up the blank space. So what was the first equation? The first equation was, the first state space equation was delta dot. Okay, so we write delta I plus 1. So that is like xi plus 1. So let me write it at the bottom so that we are not lost totally. So let me write that here again at the bottom. So that is xi, where x is the state variable, xi plus 1 equals xi plus delta t, that is your ts, multiplied by f of xi, where actually xi dot, where x is the vector, x dot is equal to f of x. there can be also u, of course. Okay, you can also take u here. That is the general expression. So let's take this as a function of u also. So it is xi comma ui. So if ui is a variable, ui is the input, remember, input to the system. If it is a variable, then we have to take the value for each index, we have to calculate it, or if we know it, then we have to include it in the code. Otherwise, if u is a constant, then we simply put it as a constant in the code. Okay, so for our model, what are the inputs? Our state space model, what are the inputs? How many inputs do we have for a synchronous machine? One is the mechanical power input, PM. What is the other one? Excitation voltage. And the scaled version is EFD. So basically we have PM and EFD. Do you know their values? Yes, we already have calculated them. This is the PM and this is the EFD. So you already have their values calculated. Okay, so let's continue the coding. So what should we write? Delta I plus 1, that is xi plus 1 equals, so that we can say we have 3x, x1, x2, and x3, because we have 3 state variables. So we write them separately because they belong to 3 different ODEs for our system. So that is TS multiplied by, so what was delta dot? So delta dot was TS multiplied by omega base. That was multiplied by omega. And so in this side, we have to write it like function of xi and ui. So it should be omega I, because omega I is a variable. Omega is a variable, minus 1. And the bracket is okay. So that's it. First equation is done. Next, the second equation is for omega dot. So we should write omega I plus 1 equals omega I plus TS. Then what did we have? We had 1 upon 2h. So we multiply 2h. So that is our 1 upon 2h multiplied by TS. That takes care of the twice h. Did we define h earlier? No. So let's now bring h here, because we will need h. So let's take h as, so that is in second also. H second. Let's take 2 or 4, whatever. So h is taken, so h is given. We assume h is given now. So we have taken some values for h. Then we have PM. Now in this model, actually PM is the input mechanical power. And unless we are disturbing the system, so PM will remain constant. Okay, that means unless we require more mechanical power input, or we want to reduce the mechanical power input, it will remain constant. Okay, so PM is not iterative. So PM remains as PM. Okay, so then what we do, PM minus, we have PT, and PT is PTI minus capital D multiplied by, and D is a constant, so there is no indexing for that, omega I minus 1. So that's for the second equation. For the third equation, we have EQ prime dot. So we write it like EQ prime plus 1 equals EQ prime I plus TS divided by, we have 1 upon TDO prime there, remember. So did we take TDO prime? Yes, we have taken TDO prime, so we leave it. So we have taken TDO prime earlier. So TDO prime into, we have EFD. EFD is another excitation voltage, or scaled version of excitation voltage. EFD minus EQ prime is one of the state variables, so it should be indexed, minus, we have XD minus XD prime multiplied by ID. Now, can anyone tell whether we should include indexing with ID or not? and the reason behind that. Yes or no, and the reason behind that. So for answering this question, you have to go into the expression, look into the expression of ID. What was ID? Because in this, when we write up to this, we see that our modeling is not actually completed yet. We haven't expressed the whole model in terms of the state variables and the inputs, because we still have some algebraic variables left inside. One is PT, another one is ID. Okay, EFD is actually the input, so we don't bother about that too much because this belongs to input. So already it is one of the inputs. So it is already represented in the form of this function of X and U. But PT, if we simply stay with PT, PT is not a state variable. It is an algebraic variable. What about ID? What is the expression of ID? Let me check back. So ID was EQ prime minus VB cos delta divided by XD dash plus XT. So if I write ID, so that means now we have to express these two, these algebraic variables, in terms of the state variables and inputs. So what is the expression of PT first? PT, we found it was VDID. VD was written in cap. So VD ID plus VQ IQ. Okay, this was the expression that we found. So we leave it for the time being as it is. Then we will come back whether they should be indexed or not. And what is ID? ID is EQ prime, but EQ prime is indexed. So we have to include the index because EQ prime is one of the state variables. EQ prime minus VB cosine delta minus VB, and VB should be the magnitude of VB. So it should be absolute of VB into cosine delta. Again, delta is indexed because delta is the state variable. So cosine delta I divided by XD prime plus XT. So this was the expression that we derived and that we used in our previous step of calculation. If you check, so this was the in line number 49. We cross-checked. We use it with the help of this, the obtained value of ID. So ID is EQ prime minus VBQ, where the VBQ is actually absolute value of VB multiplied cosine delta divided by XD prime plus XT. So it says there is a mistake in bracketing. We check where what happened with this. So probably, yeah, so here should be a bracket. So now it's okay. The bracketing is done. So now tell me, what should ID be indexed or not? This is the expression of ID in terms of state variables and constants. So because the right hand side is indexed, so the left hand side should also be indexed. So that means here in the expression of EQ prime, ID should be indexed. It should be updated in each iteration because it is a function of state variable now, and state variables are getting updated in each iteration. That's why. So similarly, we can say when we find out IQ, that would also be iterative. So let's take IQ because we need IQ to calculate PT. So let's take IQ I, and that is equals to VB sine delta divided by XQ plus XT. So absolute value of VB sine delta divided by XQ plus xt. So that is IQ. So we are still left with VD and VQ. Now, sorry, so this should be actually I plus 1, because I we are taking as the initial value of the all the variables. The first value is taken as the ith value, and the ith plus 1th value we are actually calculating with the help of the ith values here. So IQ is done. Now to complete the calculation of PT, we still need VD and VQ. So what is VD? What is the expression of VD? Because VD is, again, we see that it is a function of XQ multiplied by IQ, and IQ is indexed. So we should keep VD indexing. Similarly, VQ should be also represented in terms of some state variables. So that is EQ dash minus XD dash ID. So it is EQ prime minus XD prime ID, where ID should be indexed. Okay. So we are able to calculate PT. So that means omega part, the equation of omega. Okay, this line number 35 is done. So now PT is represented, you see, in terms of VD, ID, and VQ, IQ. And of course, the corresponding variables which are appearing in the expression of PT are also now represented, are further represented in terms of the state variables. So VQ, IQ, VD, ID, all are done. So PT is done. Anything else left? Okay, ID was left in the expression of EQ prime. ID was one of the state, algebraic variables. So ID is now again already expressed in terms of the state variables. So that is done. And now we can also calculate, if we want, we can calculate the magnitude of VT in each iteration if we want. And that is simply by taking the square root of VD squared plus VQ squared. So VD I plus 1 squared plus VQ I plus 1 squared. It is correct. Let's check. Once we run, if there is any error, we should get the error back. So let's erase these things now. We don't need them. So is it done? Probably most of the part is done. But remember, we have to plot all these variables. We have to plot all these variables with respect to time. So due to that, we have to define a time vector also. So let's take t as the time vector, and we can initialize that in this manner. So how many time steps will be there in the time vector? How many time steps will be there inside the time vector? Remember, I used this diagram. So this was my TSIM. Let's say delta. So what I am asking is this: how many points we are going to actually plot? That means, sorry?
Since total time 5 and TS is 0.001, I think it would be 5,000 point.
Yeah, excellent. So in general, we can express it like this, right? That means I'm looking for delta, the first value of delta with respect to the first value in the vector stored in the variable t. Okay, this is what we are doing. Ultimately, we'll be having 5 divided by TS, or TSIM divided by TS. Okay, and that should be the same value that we are calculating over here, TSIM divided by TS. So for all the values calculated here, we are actually getting a time value, corresponding time value, or time vector value in the time vector. So the first step that I have done is simply this: I have taken a time vector t I have initialized it actually with all zeros. All zeros. Then what I have to do, I have to increment the time vector, each of the entries. The first entry is the 0, or the first element of the time vector, that is 0. Then the second vector should be what? A second element plus TS, right? The third element would be this plus TS, and so on. And ultimately, you will finally reach at TSIM, 5 seconds. So that is the target. That means the TIth, this is if this is the TI, where I is equal to the first element. So TI plus 1, we can write TI plus 1 equals TI plus TS. Okay, that should be the updating of the T variable in each time step, in each iteration. So let's include it here. T included in the code, TI plus 1 equals TI plus TS. So that will give us the time vector updating. We have already updated the other variables. Now, what is our target? Our target is to plot it. Let's plot it, T versus delta. Let's see what is the result. At least, is it error free or not? If there is error, then we have to go for the troubleshooting. So let's run it. To path. Okay, so you see we haven't defined XD yet. Okay, you can see the error. So some of the values probably was not required earlier, but now we need it. So XD value in general, that is higher than XQ and XD prime. So let's take it as 0.8, which is higher than XQ and XD prime. Now let's try again. This is done now. So probably you are not able to see the figure window that popped up. Can you see?
No, sir.
No. Okay, so let me copy it and take it into the slide.
Sir, your voice is lower than usual. I mean, the sound of your voice.
Is it okay
Uh,
now?
Yes, sir. Now it's
Yeah, sometimes I slow down, so probably in those times you can't hear me clearly. Okay, so if you have any problem with hearing, please let me know. Okay, so let me now show you the diagram. Where is it? Yeah, okay, so there it is. Yeah, now can you see? This is my time up to 5 seconds. Do you see the diagram?
Yes, sir.
And this is my delta. What was the initial value of delta? Delta is in radians, remember. Here in our code, delta is in radians. So that is the initial value of delta. This should be equal to delta naught that we calculated in the last class. So you see that throughout the time, the delta value is fixed at its initial value, isn't it? Similarly, we can plot the other variables and we can bring them. Let's do that. So let's plot omega. What was the initial value of omega? What is the initial value of omega?
1.
1. So what is expected? Let us see whether we get that or not. So again, let me copy that and bring it to your screen, shared screen. So now this second one is actually omega. What was the initial value of omega? It was 1. So once again, the omega value, this is omega 0, and it remains constant up to the simulation time. Okay. So this is second one. What about the third one? Let's plot it in MATLAB and bring it here. So the third one is T comma EQ prime and we run it, and we bring it here. So copy, and what's that? There it is. Okay, now can you see all three diagrams? Do you see all three diagrams?
Yes, sir. We see.
Okay. So the top left is the delta versus time. So this is delta, this is time. Top right is omega versus time. The bottom one is EQ dash versus time. So what we see, one thing in common is that in each of the three cases, the variables started from their initial value, which are non-zero in each case. However, they remain constant at their initial value, right? This is the observation. These are the observations. So the system was simulated with respect to some initial operating point. So of course, the system should start to operate from that initial operating point, but there are no dynamics there because the system is simulated in such a manner that there is no external disturbance to the system. Okay, there is no external disturbance to the system. So what we will do now, we will incorporate some disturbance into the system, and we will again come back and see the responses. Okay, and we'll compare those with these three. Okay, so let's new slide, bring some blank slides. We ready, keep it ready for next figures, next set of figures. Okay, so let me actually create subplots because I have to bring several times the figures. I have to swap from this. Okay, now do you see the MATLAB?
Yes, sir.
So let me write it in terms of subplot so that I can bring everything at once to the PowerPoint slide. So the first one is delta. Then the second one is omega. So that is omega. The third one is EQ prime. So I'm using 1/3 combination. Okay, so that is EQ prime. So now what we do, because we saw that, well, our initial condition calculation and initial simulation is done. So this is actually the first checkpoint for dynamic simulation. Okay, if you have any problem, if you have left any let's say symbolic problem in typing, okay, the syntax error, MATLAB will return the syntax error. Any missing value, MATLAB will return some error. But if there are some other kind of errors, some other kind of error means, let's say for example, if you put here instead of VD, you simply write VQ by mistake, MATLAB will not catch it. Okay, so it will seem that, well, everything is done. So one way to check initially the first few steps before I start actually the disturbance incorporation, let me discuss this thing. So before you start going to the, before you run the full simulation for the dynamic model, so just run it for one iteration and check the values. So do you see the first value and second value are matched for delta, isn't it? 0.6840, 0.6840. For omega, both of them are 1. For EQ prime, yeah, both are matched. PT matched, ID. So in this way, you check the values for few iterations. And you should expect that, well, without any disturbance or before applying the disturbance, there shouldn't be any changes. Or even if the change is there, it should be, in 10 to the power minus something range. Okay, for rounding off, sometimes there is some rounding of error in MATLAB. That's why you might see some minimal level of deviation, but it should be around the initial value, even if there is some deviation. But in general, these values should be exactly same. Okay, exactly same. So you see that, well, all the values are same. And then what you do, you remove the debugging, you continue the simulation, and you get the results. So this is, and then you check the simulation, final simulation results. Okay. So then you see if though all those lines are flat, then you are done with the initial part of the calculation. That means without any disturbance, your dynamic system is working fine. Now you apply the disturbance, and now you want to see the stability issue, what is actually going on with the stability part. Okay. So if your system, if your SMIB system is stable, you will see one set of response. If it is unstable, then you will see different set of response, of course. So let's see whether our system is stable or not by simply applying some disturbance from the input end. Okay. So input disturbances could be either in the EFD circuit, that is in the field circuit. You can say, well, I would like to increase or decrease my field excitation, and I would like to see the response. This is one way. Another way, you want to see, well, if you want, you can say, well, now I want to increase or decrease my mechanical input into the system, and I want to see the response. So you can go in either way because we have two inputs. So let's say we take some disturbance variable, dist, because in MATLAB there is some already variable or already some function built in is named as dist. So we can't actually use dist exactly. So I just name it as dist1. Okay. Just any name to make sure that it looks like a disturbance, so that later on when you check the code, you can identify it as a disturbance. So we will do what? We will apply the disturbance at some point, not exactly from the beginning. We'll apply the disturbance. So dist1 has to be defined now. So let's say we define disturbance in such a manner that if we apply some condition, if your I, that is the index, is greater than, or we start with less than, if I is less than some time, okay, let's say dist time, less than dist time by, of course, it is index. So dist time is a time. When you divide it by TS, it becomes an index. So if dist time is, I is less than that, then your dist1 is 0. Okay, so dist1 is equals to 0, else you give some value to dist1. Let's say any value 0.2 in per unit, because you are giving disturbance in PM. What is the initial value of PM? That is equals to PT. Okay, so you have to keep in mind that what is the actual value you're dealing with, and based on that you have to apply some reasonable value of disturbance. Okay, because all are in per unit, so your PT is probably, it was 0.9, sorry, 1 per unit. So 0.2 means you are actually increasing or decreasing 20% mechanical input. Okay, 20% of that, and you should end the condition if else condition is ended here. Now we see what is the response, or whether there is any other. Okay, so you see we forgot to define dist time. Okay, because here the condition includes dist time. So let's define dist time. Our total simulation time is 5 seconds tsim. So your dist time should be within that, from 0 to 5, any value. If you select it to be 0, then exactly from the beginning your disturbance will be there, but let's apply it after some time. 1.1 second. After 0.1 second, we apply the disturbance. Okay, so let's bring it to your, let's bring it to the PowerPoint slide, and let's discuss what is going on. Okay, can you see? Oh no, that's new share. So the new share should be this one. Okay, now can you see this one? This is, so you see actually some oscillation, right? You see some oscillation. This is your EQ prime, the third figure. This is your first figure is delta. Second figure is omega. So what is happening now? Actually, the total dynamics, it will take probably few more cycles to capture the dynamics. Okay, it is difficult to say what is actually going on, but looking at the EQ dash, it doesn't look good, right? I mean, you see that EQ dash is falling continuously. It doesn't look good. Looking at omega, it seems that there is a little decay. There's a little decay there. Looking at delta, it is actually it is again difficult to identify because the whole thing is actually moved up. Okay, the whole thing is going in that trend. So probably for finding out any further insight out of this, we have to probably increase our simulation time. So let's go back. Let me do it. So what I will do, I will take, let's say 10 seconds and let's see what happens. It's still not that much. Okay, let me do it the background, and when I am satisfied, I will bring it. Okay. So just have your patience. Yeah, now it looks a little interesting. Okay, let me do it a little further. Let me make it 30 seconds. Okay, let me show this now. This is a bit more interesting than the previous one. So let me bring it into the PowerPoint slide. It is the first one. Okay, now can you see? It is simulated for 30 seconds. Just what I have done, I have increased the total simulation time, TSIM. I have made it up to 30 seconds. So now can you see? Hopefully you can see. So what you see, can you explain the profile? So now it seems that, well, EQ dash, this is EQ dash, this started from its initial value. Due to the disturbance, increase in PM, mechanical power input, the EQ dash actually reduced initially, but then it seems that, well, it is settling down. Of course, it's oscillating, but it's settling down to some value, okay, to some average value finally, okay? It seems like that. It has settled down around 20 seconds. Okay, so it took a long time for it to get settled. I mean, by settled means to some average value, some oscillatory value, but the oscillation is constant. Oscillation is not increasing anymore. Omega, of course, after the disturbance, which was applied at 0.1 second, now because the time scale has been increased, the time of simulation, so 0.1 is actually not distinguishable from this diagram, but we know that we applied at 0.1 second. So you see there is a clear, I mean, profile which shows that ultimately you expect that after probably a few more cycles, okay, many cycles, several cycles, after several cycles, you expect that this omega probably would go back to 1. We'll see that. We'll try to bring that to 1 quickly. We'll discuss how just in a minute. And delta actually, yeah, delta actually initially it increased, then you see it is coming to good shape. Okay, it is again coming to some closed bound. So we can say that the responses are getting bounded slowly. So which means in a sense we can say the system in this current scenario is stable, but the stability is not in a good shape. Okay, by stable means if you give some bounded input, you get some bounded output. This is one way of defining stability, and that is BIBO stability. We call it bounded input, bounded output stability. This is one way to define stability. But to be more clear about the scenario of stability, what we can do now, we can play with the damping term. Remember, we had a damping term. And in general, if we apply positive damping, to the system, then we expect this oscillation to decay at a faster rate. Okay, so let's see, let's check it. So what we will do, we'll go to the MATLAB and we will intentionally increase the damping term and see what's the effect. It was 0.5 only. So simply we make it 5, okay, 10 times. and see what is the response. Excellent. So let me show you. It's excellent. Okay, so copy figure, bring it to where? So here, a new slide. Okay, so let's paste it here, the new one, remember, with d equals to 5. Now you see?
No, sir, you have to share.
Okay, probably the sharing is somewhere else. Now can you see?
Yes, sir.
Okay, so you see the change simply by changing the damping. Although it's for demonstration purpose, there is a huge intake out of this change of value in D. It means if you somehow can incorporate the damping, or you can attach some device to your system, power system, which will provide you some positive damping. We are increasing the damping, remember. D, the value of D itself is positive. So what we have done, just for demonstration purpose, we have shown that, well, if we increase D, my system is, the oscillation in the system, the initial system oscillation, which was larger here for a small value of D, such as D equals to 0.5, we can get rid of the oscillations very quickly. You see, even in this figure, even after 30 seconds, you can't say exactly when this system will settle down. Okay, but we had some rough idea that, well, the system is going to be settled after several cycles of oscillation, but it would take much long time. So if we somehow can incorporate the damping term, or if we can incorporate some damping torque or damping power into the system, positive damping power, then this is the benefit. And it is clearly visible from here. Okay, so you see the EQ prime oscillations have died out. Now EQ prime has settled, actually. There is no oscillation. The value is reduced in EQ prime. The delta value, okay, it started from some initial value, of course. It's not, we can't figure out from here what was the initial value, but that value is available in the code, of course. So delta is settling at some steady state value, and of course omega should settle at 1. There is no other choice for omega because it is synchronous machine. So for synchronous machine, if the system is stable, you should expect omega to be at exactly 1 per unit. Okay, so this was the few of the things that I wanted to show in today's lecture. Actually, my target was a little bit more. I wanted to introduce the linearization also, but probably I will leave it for the Eid vacation. Yeah.
If we want to get the stable very few time, I mean, if 10 seconds or 5 seconds, what should we do?
I don't get your idea. If we want to,
if we, since look here, we are getting the delta 20 second, the stable position in 20 seconds.
Yeah, if you want to get it further, there are few things you can do. We'll do those things later on. Okay, we'll do those things later on, but this is because this is the simplest model. Actually, what you can do, you can incorporate system further components. You can add up further components in terms of supplementary control. Okay, that is known as supplementary control. One of the technique that is used for actually getting rid of these oscillations is, of course, introducing damping into the system by some additional device or by some additional control technique. Okay, remember, there are no controllers. Okay, have you figured it out, or have you noticed that there are no controllers in our system? There is no control. This is an open loop system. So for an open loop response, this is quite acceptable. This is very much acceptable. This is open loop response. This is open loop stable. There is no control. There is no feedback. We are not measuring anything. We are not feeding it back, and we have not implemented any control. So for reducing it any further, for reducing the time, okay, that means, let's say around here, I want to make it stable after one oscillation. I want to look it like this. So this was the initial value. I just want it like this. This is probably what you are meaning. Okay.
Yes, sir. All right.
Let's say 0.1 second, the disturbance is started. At 1 second, I want it done. Okay, I want it done. There should be no further oscillation. One way is to increase the damping. Another way is to implement control. Okay, so these are the few of the techniques, of course. Another thing or another family of devices is there, and that of course will take help of these two. Okay, the FACTS device. You implement FACTS device and you produce some D, positive D, and you inject it into the system. You introduce some FACTS device and you control its parameters such as the variable reactance or variable injection of reactive power into the system, etc., etc. So the control itself is a huge domain. Okay, the power system control. So here, this belongs to power system control. And this is a vast field of research, power system control. You can apply linear control, you can apply AI, you can apply fuzzy logic, you can apply optimization, you can apply conventional PI control, you can apply nonlinear control, you can apply adaptive. It's a big list. Okay. So your question is short, but the answer is not short, unfortunately. Okay. There's a huge field for, doing what you are actually wanting to do. Okay. To take it much closer to the disturbance application time. So when you apply the disturbance, before disturbance, system should remain at the initial point, and then it will start to oscillate, and you try to make it settle down as quickly as possible. Okay. So any other question? So that will be left for the control part. When we will design some control, then we will see how we are going to do that, how we are going to even further improve the responses. But this is how you actually simulate, and you observe the response, and you can see whether it is stable or not. Now let's see another important thing, because we still have 6 minutes. Let's see how it might look if the system is unstable, right? Stable is fine. We are in a good world. Everything is fine. Everything is good. Now let's look at some bad phenomena. This is a good phenomena. By increasing D, we have achieved that. Now simply what we do, we go to the MATLAB, and again, this is just for demonstration. Okay, where we have come to the same slide probably. Where is MATLAB? Okay, here it is. So here, yeah, do you see the MATLAB now?
Yes, sir.
Simply we make it negative damping. Okay, so we go back to the previous value of 0.5, which was positive at the beginning, and simply we put a minus sign, and let's see whether it is unstable. Just what we are trying to see, how it might look in case of instability. Okay, this is just again for demonstration. So we run it. Okay, we have got it, what we wanted. So let's copy that. And again, okay, let me complete the pasting first. We'll go to the new slide. Remove everything and bring your figure there. Now we are ready for the sharing. Okay, do you see now? So what is happening? How is the profile? You see EQ dash is oscillating again, but when D was positive, actually the oscillation was actually settling to a fixed value, right? It was settling around some average value. But now what is happening? You see it is continuously increasing. Can you follow the profile of increment? The oscillation is there and it is increasing with time. So if you continue further, you will see that it is further increased. The magnitude of the oscillation, I mean. Similarly, your delta, it is going to unbounded case. Your omega, it is increasing with respect to time. So this is known as unstable scenario. Why it's unstable? Because you see, if you continue the operation of machine in this under this scenario with this kind of capital D value, then you are in danger, because your omega, you see, it is in per unit. So as time will progress, this might go well beyond your control. Okay, and of course there are protections for helping you out, for saving your system, for saving your machines, saving your components. So the over voltage detector, sorry, the over speed will be detected, and ultimately your system should be tripped from the remainder part of the network. Your generator should be tripped. So all these three variables are actually internal to your machine. Remember, internal to your machine. These are not external variables. These are not available in the network. Delta, it is the internal angle inside the rotor. Omega, yeah, this you can measure quite easily, but this is again related to the shaft of the machine. This is not available in the external part of the electric network. EQ prime, this is completely some internal variable. You can't probably even measure that, but you can calculate that, you can plot that. Measurement is not possible. It's not straightforward. And again, similarly, we can also plot some other variables, as I said, because we have seen already, we can plot delta. So as I said earlier, so we can plot now PT. Okay, because PT is included in our code. So we can see the profile or the trajectory of PT. We can see the trajectory of QT. We can see the trajectory of IT, isn't it? Everything are available to us. So all other things you can simulate them, you can plot them, and you can see what is happening with them. So this is what actually where I should stop, because we don't have any time left for today. But I wanted to at least introduce the linearization part, but we don't have time. Sorry for that. So inshallah, the linearization will be taken after the Eid vacation. What is the essence of linearization? First, we have to identify that our model that is developed here is a nonlinear model. This model, the third order model, is a nonlinear one, isn't it? Do you agree or not? Okay. No answer. That means you are in between. Is it a nonlinear model or a linear model? So for identifying that, what you have to do, you have to look, okay, by looking simply at this, you can't tell because you have some algebraic variables. So you have to look at the algebraic variables expressions. So ID was what? EQ dash minus VB sine delta divided by something. Okay, these are reactances. I don't remember, but it is there in your slide. We are not interested there because we already have got something which is nonlinear, isn't it? So ID is actually having some part of expressions which is nonlinear. PE, when we express it, you will see it is VDID plus VQIQ. VDID plus VQIQ. And when you expand these expressions in terms of state variables, you will see that ID, IQ, when you multiply with them with some other expressions of VQ and VD, which are again functions of ID and IQ themselves. So all in all, this model over here is a nonlinear model. So what we will try to do next, we will try to derive the small disturbance model or the small signal model for this nonlinear state space model. So for doing that, or for achieving that, we have to adopt the linearization technique, which is very simple. We simply will apply the Taylor's expansion, and we will expand the we'll use the Taylor expansion, and we will only take up the linear terms. The higher order nonlinear terms will be ignored. So our next target is to study the small signal model, to have a linearized state space model, which would look like this, something like this. So x dot equals ax. So that is our next target. Inshallah, we will take it. We'll start it after the Eid vacation. And y equals cx plus du. So starting from a nonlinear expression f x dot equals f of xu. This was the expression we started with, the steady space model expression. I mean, y equals h of xu. This was the output equation. So from this nonlinear model, we will go to this linear model, and we will call it the linearized steady space model or the small signal model. And then we'll again apply the same disturbance, and we will try to find out whether the responses are identical or not. This is one target. Another target, we will start to design some control or implement some control for this. But before that, we will take the exciter model. We'll try to find out that from where actually we would get this EFD, or will there be any dynamics associated with EFD or not. That will be taken in exciter modeling later on in the course. Then also PM, this is mechanical input. This will come from the turbine side. So we will go for turbine modeling. Turbine input comes, or the control associated with the turbine is the governor. So we will also take the governor modeling. And then inshallah, if we have some time left, we will probably look at some of the facts device modeling. Okay. And I think by then our time would be over. So inshallah, we will at least try to touch some of the facts device. That is our target for the time being. If we still have some time left, okay, another thing is left. We also have to model the loads. Okay, dynamic load modeling, that is also there. And this is actually, in a nutshell, this is the syllabus that is left. Okay, that is the tentative syllabus that is left. Okay, any question? No question.
No,
So
sir. Sir, which date we may start, sir? After it.
I think I have shared with you the in the Google Classroom. I think I thought I have shared the schedule.
26
Yes, sir.
the official day of class started, but perhaps we have to go for 27.
Okay, I think, yeah, 26th. Yeah, I get it now. So I have opened the calendar. So 26th is the Monday. So our class will be on Tuesday. First class will be on Tuesday after the break. So it would be 27th at after Maghrib, I mean 7:15 around that time. Okay. So
Okay.
Rihad, our class would be on 27th, inshallah, again. So till then, have a nice break. Okay. And we should pray for each other, so then we can stay safe by the grace of Almighty Allah. Okay then, so see you inshallah, and Eid Mubarak to everyone.